This is a fat rhombus. Two angles of 72 degrees, two of 108, a simple diamond shape, just two shapes are needed. Watch the tiles snap into place, growing outward. Most people assume any tiling repeats. Bathroom tiles do. Honeycombs do. Surely these must too. But they don't. The red box scans for a repeating block. It fails. Any block, any size, no match, no repeat, not in a meter, not in a billion kilometers. Here is the question. Can two shapes cover an infinite plane without ever repeating? Take a guess, yes or no, and drop it in the comments. 5 steps, 2 tiles, a hidden golden ratio, an inflation rule, the proof, and a real-world echo. Chapter 1. The fat rhombus on the left, the thin rhombus on the right, both share the same edge length. These are the only two building blocks we need. Now the angles appear. The fat rhombus has acute angles of 72 and obtuse angles of 108. The thin rhombus has 36 and 144. Every edge is length 1. Two fat rhombuses slide together. A 72-degree corner meets a 108-degree corner. Together they form a straight edge. 72 plus 108 equals 180, perfectly straight. Here is a circle divided into 10 slices of 36 degrees. Every angle in both tiles is a multiple of 36. 72 is 2 slices. 108 is 3 slices. 144 is 4 slices. All angles are multiples of 36. This is tenfold symmetry. But here is what almost everyone misses. This symmetry hides the most famous number in mathematics, the golden ratio. You cannot unsee it. Chapter 2. The golden ratio, hidden in Penrose tiles. Look at the fat rhombus again. Angles 72 and 108. Side length 1. Now we draw a diagonal through the acute corners. That long diagonal has length phi, about 1.618, the golden ratio. A diamond with angles 72 and 108, and its diagonal equals phi. Phi is one of the most famous numbers. 1 plus root 5 over 2, it appears in sunflower seed heads and pinecone spirals. And now inside a simple diamond. The key is the pentagon. Its diagonals meet at 36 and 72 degrees, and each diagonal is phi times a side. Now the thin rhombus. Its short diagonal measures 1 over phi, about 0.618. The fat rhombus gives phi. The thin rhombus gives 1 over phi. Mathematical inverses. Where does phi come from? The long diagonal is 2 times cosine of theta over 2. The short diagonal is 2 times sine of theta over 2. For the fat rhombus, 2 cos 36 gives phi. For the thin rhombus, 2 sin 18 gives 1 over phi. Watch as we build the golden spiral. Starting with a golden rectangle, we carve out squares. Each time we remove a square, the remaining rectangle is still golden. This never ends. It is self-similar. But why should a spiral matter for a tiling? Hold that thought. In 2 minutes it becomes the rule that builds an infinite floor. The fat rhombus carries phi. The thin rhombus carries 1 over phi. These angles belong to the pentagon, a shape drenched in the golden ratio, but a ratio alone builds nothing. You need a rule, and it is almost absurdly simple. Chapter 3. The Penrose inflation rule explained. How do two tiles build an infinite non-repeating pattern? The answer is a rule called inflation. Watch a single fat rhombus. It subdivides into 3 smaller tiles. 2 fat rhombuses and 1 thin rhombus. 1 tile becomes 3. This is inflation. Now the thin rhombus, it subdivides into 2 tiles. 1 fat and 1 thin. These are the only rules. Fat becomes 2 fat plus 1 thin. Thin becomes 1 fat plus 1 thin. But here is where it gets stranger. Start with 1 fat tile. Inflate it. 2 fat, 1 thin. Inflate again. 5 fat, 3 thin. Again. 13 fat, 8 thin. Again 34 fat, 21 thin. Again 89 fat, 55 thin. Watch the counts. They are climbing towards something famous. Look at these numbers. 1, 2, 5, 13, 34, 89 for fat. 0, 1, 3, 8, 21, 55 for thin. Interleaved Fibonacci numbers. Every ratio drifts toward phi. The Fibonacci sequence appears everywhere in this process. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. And because phi is irrational, the ratio can never be a fraction of 2 whole numbers. It never settles. That is why the pattern can never repeat. But why does an irrational ratio forbid repetition? Most people get this wrong. Chapter 4. Periodic versus aperiodic tiling. Phi is irrational, so the ratio can never be a fraction. But let us see what periodic means. Here is our Penrose tiling, frozen. Why can it never repeat? Let us build the intuition. First, a periodic pattern, a grid of squares. Pick a 2 by 2 block, shift it left, right, up, or down. It lands perfectly on an identical block every time. That is what periodic means, a translation that maps the pattern onto itself. Same story with the honeycomb. Pick a block, shift it, and it matches perfectly. Bees build their hives this way. Most tillings in nature are periodic. It feels like the normal way patterns work. Now return to Penrose. Watch the red box scan. We try every block, every size, every shift. The result is always the same. A red X, no match. Another position, no match. No translation maps the tiling onto itself. This is non-periodic. The irrationality of phi has locked out periodicity at the deepest level. If this is starting to click, consider subscribing. The best part is still coming. And tell me in the comments, did you expect an irrational number to forbid repetition? Strong intuition. But can we actually prove it? Let us find out. Chapter 5. Proof that Penrose tiling never repeats. We have the intuition. Now let us prove it. 2 independent proofs. The key is self-similarity. Watch the scale breathe. Inflate, tiles split. Deflate, tiles merge. The result is always still Penrose tiling. This property drives the proof. Here is the promise restated. 2 shapes cover infinity without repeating. Now we prove it. Proof a contradiction by deflation. Suppose Penrose is periodic. Then a finite repeat unit reproduces the whole pattern by translation. Watch the boxes on the right. Now deflate. Merge small tiles into larger ones. Self-similarity means the result is still Penrose. Periodicity means it is still periodic, but the repeat unit shrinks by a factor of 1 over phi. Deflate again. Smaller, again. Smaller. Each step the unit shrinks. Keep watching, but stick with me. At the end there is one more surprise. This pattern shows up in real matter and it won a Nobel Prize. Now look at the final box. It is smaller than a single tile, but a repeat unit must contain at least one complete tile. Contradiction. Therefore Penrose is non-periodic. That is proof A. Proof B. The ratio argument. The ratio of fat to thin tiles converges toward phi, approximately 1.618. In any periodic tiling, fat and thin counts in one repeat unit must be whole numbers, so their ratio must be rational, a fraction of 2 integers. But the Penrose inflation rule forces the ratio toward phi, which is irrational. Rational can never equal irrational. Therefore no periodic repeat unit exists. 2 proofs, 1 conclusion. Proof. A uses geometry and infinite shrinkage. Proof B uses algebra and number types. 2 different paths, the same destination. Independent lines of reasoning reinforce each other, leaving no room for doubt. This is how mathematics works. To summarize, 2 simple diamond shapes, 1 irrational ratio, phi, an inflation rule for endless non-periodic patterns, a rigorous proof. The non-periodicity of Penrose tiling is mathematical certainty, but how do you place these tiles without mistakes? For that, we need matching rules. Chapter 6. Penrose matching rules. We have the tiles and the inflation rule, but you cannot just throw them together. Look at the edges. Some edges carry a single red arc, others carry a double blue arc. These markings are not decoration, they are rules. Watch a mismatch. A red arc meets a blue double arc. Rejected, a red flash, a red X. This arrangement is forbidden, the rules are strict. Only matching arcs may join. Now a correct match, red meets red, blue meets blue, a green glow signals acceptance. These local rules force a global outcome. The matching rules do not prevent complexity, they guarantee it. Chapter 7. Quasicrystals and Penrose tiling, that surprise I promised. Watch the Penrose tiling dissolve into a diffraction pattern, tenfold symmetry just like the tiles. In 1982, Dan Shechtman discovered quasicrystals, atoms in patterns that never repeat. Penrose on the left, diffraction on the right, they pulse together. Nature used this structure all along. In 2011, Schechtman received the Nobel Prize in Chemistry. Two diamond shapes, the golden ratio, and a pattern nature itself uses. Let us close with the big picture. Two shapes, one irrational ratio, a proof that repetition is impossible, we asked. Can two tiles cover infinity without repeating? The answer, yes. From tiles to golden ratio, inflation, proof, matching rules, and quasicrystals, a Nobel Prize discovery. If atoms break the rules of repetition, what other impossible patterns hide in plain sight?